Okay, this is the M1 paper for January 2021. It's question number 8. And as you can see, if we just scroll down and look at this question, it is a connected particles question, but it also involves an inclined plane. There's already hints to tell me that suvat is going to be involved in this. We're going to be resolving forces, a lot of detail, a lot of work in here. And as we can see, this is a 17-mark question, which is okay. It's at the end of the exam. And actually, this is such a standardized one that I'm going to put this into my how to do videos as well. But let's have a look at it and see what we've got. So before I get started with my diagram, just a quick look at it to say we've got a particle A here and a particle B there. B is heavier, and it actually tells me in the question that B is going to descend. So what we're going to have, quickly before I get started, this is going to go down, this is going to go up here. We've got a frictional force opposing that motion there. When B actually ends up hitting the ground, A will then continue on its journey, but without the tension dragging it up. And they're going to ask me all sorts of questions about that. So let's get started with doing it. What I can't do is to try and draw my diagram, all my forces on that diagram. It's not big enough. So I'm going to use this little bit of space down here. And I'm going to draw my diagram out so I can put all my forces on nice and neatly. And then once I've got all my forces on there, I'll resolve them into the directions that are going to be useful. So we've got that the angle there is alpha. This is my particle A, which is connected, or rather goes over the pulley, and then comes back down here to my particle B. Right, let's just look at A for the time being. A has a mass of 2 kilograms, so it has a weight of 2g acting down there. Because it's sitting on this plane, we have our normal reaction there at 90 degrees. And as we said, we may as well put this on now. We know it's going to be going in that direction and in that direction. So that informs me that friction is going to be going there. May as well put our tensions on. We're going to have a tension in the string here and a tension in the string there. Now let's just focus on particle B for a second. That's got a weight of 4g there. So once we've done that, that's all my forces on my diagram. What I now need to consider is, as I said previously, I'm going to be interested in F equals ma in this direction. So this force here at the moment is a bit of a pain. What I want to be able to do is to resolve it perpendicular to the plane and parallel to the plane. Well, okay, let's just quickly say that angle there would be 90 minus alpha. This is 90 degrees in here. So this angle here would be 90 minus alpha, which means that this angle here would be alpha. We just put it in. It happens every single time, but that's the reason for it. And if we've now got this triangle here where this is 2g and this is alpha, then I can resolve these forces into 2g cos alpha and 2g sine alpha. As I said, this is a classic question, so that really, so far, shouldn't have caused us any issues at all as we're going through and doing this. One of the other things, the reason I chose it as being a classic question, is this tan alpha equals 3/4 means, right, okay, let's do this over here. If tan alpha is equal to 3/4, then I could construct this triangle here where this is alpha, this is opposite, this is adjacent. Using Pythagoras, we get 5 there, 3, 4, 5 triangles. A lot of you will know that, otherwise work it out using Pythagoras. But this means then that tan alpha equals 3/4. I can now, from the diagram, say what sine alpha and cos alpha are. Sine alpha, opposite over hypotenuse. Cos alpha, adjacent over hypotenuse. So I've got rid of that little bit there. And while I'm at it, the other piece of information I haven't said so far is that mu is going to be equal to 1/4. Right, brilliant. Once I've got that diagram done then, I'm now good to go with what I'm going to do. Let me explain it to you first, and then we'll actually go through and do it. What I'm going to do is I'm going to look at particle B. Let's put particle B on the actual diagram as well. Particle A is there. Look at particle B, and I'm just going to do resolve vertically, F equals ma. I'll get an equation there. That's the simple one. That's why I do it first. If I then, sorry, I just got rid of A. If I then look at particle A, the standard technique that I do is, first of all, I'm going to resolve in that direction. I'm just going to get that R equals 2G cos. Once I've got R, I'm going to be able to say F equals mu R. So that will then give me F. And once I've got F, I'll then be able to do, with those three forces, F equals ma, and be able to get a second equation of motion. Right, that might sound quite complicated when I'm doing it without you seeing the calculations going on, but now that's just explaining it to you. I've now got to explain it to the examiner. So in explaining it to him, you get a second description of what we're doing. This is B, this is A continued, isn't it? So consider particle B. I'm telling the examiner absolutely what I'm doing. Consider particle B. Resolve vertically. F equals ma. Let's look at what I'm talking about. I'm talking about this bit here. We know that it's accelerating downwards, which means that this force must be bigger than this force. So when I do F equals ma, I'm going to get 4g minus t equals 4a. Not a surprise to me at all. Shouldn't be a surprise to you. The other equation of motion I'm going to get later on is going to be t minus something. And when I get that one, then this one and this one will be solved simultaneously by adding the equations. I know all of that before I even get started. You should as well, if you're a really strong candidate here. Right, so I finished with particle B. That's why I did it, because it was nice and easy to do that bit. Let's now consider particle A. Again, telling the examiner what I'm doing. It takes me a couple of seconds to do, but I think this is really useful when I look back at this. When you look back at just the written version of my answer, it's quite clear each step what I'm going to be doing. So consider particle A, and now I'm going to start off, I did say this already, but by resolving perpendicular to the plane. F equals ma, and I'm going to get R equals 2g cos alpha. Don't worry, let's go back and have a look at what I'm saying there. So what we're saying here is perpendicular to the plane. Okay, we know that the particle is just going to go smoothly up in that direction. It's not going to be jumping up and down. So the forces must be in equilibrium there. This force must be equal to this force. So even though I say F equals ma, I'm just going to say R equals 2g cos alpha. And remember, cos alpha is going to be 4/5 there. So all of these little bits coming into play. So R equals 2g cos alpha, which is 2g times 4/5, which is 8g over 5. So I knew before I did that the reason I was going to do that was because my next step was going to be F equals mu R. If they'd wanted to, they could have made this a bit simpler by either having a smooth plane and there was no F acting there, or by saying F is equal to 10 newtons or 100 newtons. Then I could have got away with not having to do the F equals mu R, but actually, no, they want you to do this, don't they? So F equals mu R, F is going to be mu lots of what we just found, 8g over 5. So F is going to be 2g over 5. Right, brilliant. Well, the whole point about doing that was so that I can do this last stage. Resolve parallel to the plane. Do F equals ma. What am I talking about now? I'm now talking about in this direction, we're going to have F equals ma. this is going to give me my equation of motion number 2. So F equals ma in this direction. What have we got going on? Well, first of all, we've got this accelerating that way. So that means that the t is going to be bigger than these two. So it's going to be t minus f minus 2g sine alpha. And we've just worked out what f is. So let's go ahead and do that. So t minus f, sorry, let's make it a bit bigger for me too, minus 2g sine alpha is equal to 2a. Remember the mass here is 2, but we know what f is. F is, we just worked out 2g over 5. And 2g sine alpha is 2g, but we got sine alpha from before, 3/5 is equal to 2a. So tidying all that up, t minus, what's that, 8g over 5 in total is equal to 2a. There's the second equation of motion. And I was expecting to have this situation. I'm going to bring the equation of motion, the first one, down and put it underneath it just so that we can see what we were doing. We had that from before. And I know I'm just going to add those two together now to solve them simultaneously, because I always do. I always going to have, these things might be different, but I'm always going to have t minus and something minus t on these connected particles. So if I now do 1 plus 2, I'll get that the t's will cancel out. What am I going to get there? I'm going to get 12g over 5 is going to be equal to 6a. Yeah, 4g, take away 8g over 5. Yeah, it's 20g over 5, take away 8g. 12g over 5 is equal to 6a. Okay, so acceleration is equal to 2g over 5. Sometimes that's what they'll ask you to do. Or if this 9-mark question here, look, there's a big old 9 marks there. They could have split this up into lots of different bits. Could have been find the acceleration, then find the tension. It could have been find the equation of motion, find the other equation of motion, find the acceleration, find the tension. But no, they want to give it all to us as a big 9 marker. So I've got the acceleration, but I wanted the tension. So I'm going to use equation 1 just because there's less to use on it. So from equation 1, we actually have that t is 4g minus 4a, if I just rearrange that. So that's going to be 4g minus 4 lots of 2g over 5. So that means that the tension is going to work out to be 12g over 5. 9 marks for that first bit. Okay, still quite a bit of the question to go. So it says, on hitting the ground, B immediately comes to rest. Given that A comes to rest before reaching the pulley, that will always happen. They're not going to have it hitting the pulley. It would cause all sorts of problems modelling. Find in terms of H the range of possible values of D. Wow. So again, this is an interesting question here. Just straight in with the 7 marks. They're not trying to help me out at all here with what's going on. They've just said, yeah, just get on and do it. So let me just explain to you what I'm going to do before I get started with doing it. And it's now basically going to be considering this particle A here. What happens to A is that when B goes down and hits the ground, A will move up, obviously. Well, A will move up because it's being pulled up by this tension here. So that part of the journey, we're going to have to consider that as a separate situation too. When B does hit the ground and A is at this point here, B doesn't move anymore, but A is already moving with a speed, and it doesn't just suddenly come to a halt. There's no tension dragging it up anymore, but it will continue up for a little bit under its own momentum before eventually it stops because it's not being pulled up anymore. It's actually decelerating from that moment onwards. And what they're going to want us to do is to consider, I didn't put the H and the D on the diagram, but how far up there it actually manages to get. So I've explained that to you. I've now got to explain to the examiner what's going on. So I'm going to say for part B, for motion of A while the string is taut. So again, let's just explain what's going to go on here. I'm not going to put this on my diagram. This is just for you guys. A is going to go from there to there while it's being dragged by the string. And we know from the original diagram that it will move a distance h, because that's how far B moves. B hits the ground. Then it will move a further distance, but under its own state with no tension. It's going to move a further distance there. And one of the things that we understand is that here the acceleration is going to be what we just found, 2g over 5. Here this will have a new acceleration, and actually the acceleration will be negative. It will be slowing down from that moment. We knew it's going to do a new distance there, but the one thing that is going to be constant here is that the final velocity of that motion will be the initial velocity here at this point. This v here is going to be the same as this u here for my new motion. So hopefully that makes a little bit of sense to you. Let's just go ahead and do that. So the first thing I'm going to do is consider the motion while the string is acting. So suvat, what do we know happens? Well, we know it moves a distance h because we've just said that. We know it started off from rest. It's going to get to this final velocity that I'm interested in. And we know it was accelerating with 2g over 5. Time I'm not interested in at all. Okay, that's a classic, as I've said previously, suvat question where I'm going to use s, u, v and a. So I'm going to use v squared equals u squared plus 2as. V squared equals u squared plus 2as. I've got those ones, and I want to work out what v is going to be. So v squared is going to be nothing plus 2 lots of 2g over 5 lots of h. So I'm going to get that v squared equals 4gh over 5. Now, yes, I can find v is equal to the square root of that, but actually I'm only going to be interested in, so I'll put it in, but really the v squared is the bit that I'm going to be interested in because of later on work. Okay, so all right, fine. That's the speed then that A is going at when the string snaps, when the B hits the ground, sorry. So when B hits the ground, I now need to find the new acceleration. So the next thing, again, tell them what I'm doing. Once B hits ground, no longer have t, therefore need the new acceleration. So this is a pretty classic question. If we go back to our diagram here, okay, we're talking about F equals ma in that direction. We're talking about this equation of motion, which was this equation of motion. And all we're saying is, in that, there is no longer a t. There is no longer a t. So I can work out the new acceleration relatively straightforward. I don't need to draw a new diagram out or anything. Let's explain it to you. Let's explain it to the examiner. So I don't explain it to the examiner. Once B hits the ground, there's no tension. I'm trying to work out my new acceleration. So again, I'm not going to put this on, but just to finally explain it to you. That's what I've got, but where there's no t there. Okay, so if there's no t there, that's what I'm going to have. This is going to give me a negative acceleration. Yeah, of course it is. The whole thing's going to slow down to 0. So actually, if we don't get a negative acceleration here, minus 4g over 5, there'd be something wrong. So yeah, that's sort of given me a little bit of confidence that A works out to be minus 4g over 5. Right, I'm now going to consider that second motion. So again, for motion of A, after B hits the ground. So we can use suvat. It's going to be a constant acceleration, or in this case, deceleration. So S, how far does it go? I don't know. That's what I'm interested in. U is going to be that speed there. The final velocity, the minute the string breaks, that's going to be the velocity there. Now, as I say, I can write it out as this 4gh over 5. But I'm going to be using u squared in a minute anyway, so the square root's going to disappear. This motion is going to be A moving up till it stops, so V is going to be equal to 0. We've just found our new acceleration. Not interested in time again. So what I can now do is I can use this to work out what the distance travelled is, what the S is going to be. So if we put this into V squared equals U squared plus 2AS, I hope you're all still with me. We're going to get 0 squared is equal to 4gh over 5. That's why I wasn't too worried about the square root thing. That's going to be squared again. Plus 2 lots of this new acceleration minus 4g over 5, all multiplied by S. Right, let's not make a mistake algebraically if we've got this far. So I'm actually going to call this 0 equals 4gh over 5 minus 8g s over 5. 8gs over 5 equals 4gh over 5, and everything can cancel, a lot of it can cancel. We actually get that S works out to be equal to h over 2. Wow, such a lovely, neat answer to that bit. Hopefully that's going to make sense to me then. So what happens to this object is it moves h as this one hits the ground. It then moves another h over 2 there. So the distance d, d has to be greater than 3h over 2, h plus h over 2. Wow. Okay, so we're on to the last part, part C. This is a little bit unusual, but using sort of the same ideas as we have before. And I've got a video on this which just explains to you or reminds you of all the modelling bits that we need to be aware of. They write it in a slightly different way here, though. Rather than saying describe an assumption or saying what does the fact that the string is inextensible mean, they actually say if you were trying to make the model more realistic, which of the physical factors could we take into account? So they're actually going back and saying, you know, these modelling examples that you've got here. So we've got a light string, we've got an inextensible string, we've got a smooth pulley. Well, none of those things really exist. Strings do have weight. There's some sort of extension in them, and pulleys are never completely smooth. So you're just going to pick one of those and then say, if it was more realistic, the pulley might not be smooth, the string might not be extensible, or the string does have a weight. Only choose one of them. Don't choose anything else. They're the ones that the modelling is based on. So I'm just going to put in here the pulley may not be smooth. But as I say, we could have chosen the other ones. And if the pulley would not be smooth, then there could be friction. But any one of those three you could have chosen just to finish that one off. And yeah, that's a big, big question. But as I say, very, very standard. And their expectations from the fact that they haven't broken it up into the little parts is that you are capable of doing something like that. So keep coming back and looking at this question. Hopefully it makes sense.